Hello everyone. Today we're going to talk about radical expressions and some graphs associated with radical functions. When you see an expression looking like this, the square root of some number n, there is a number in here which we usually don't like because it's 2. And the square roots are so common that we just decided we'll leave the 2 out if the root that we're looking at is the square root. And that number there is called the index. This right here is called the radical sign. And the number that we're finding the square root of is called the radicand. So for real numbers n that are greater than 0, when we say the square root of n, and of course that's how we write this, we read it the square root of n is basically any number whose square is n. So that brings us to a situation like this. We know that if we take 5 and square it, that gives us 25. So this means 1 square root of 25 is 5. But I also noticed that if I take negative 5 and square it, I also get 25. So that brings me to the understanding that if the square root of a number is any number whose square is that number, then 25 isn't just going to have 1 square root, it's going to have 2 square roots. And the way we say that is we say the positive square root of 25 is 5. But there's also a negative square root of 25, which is negative 5. We don't want to put the negative inside the square root. It stays on the outside. So this positive square root is called the principal square root. Of 25. The negative case is called the negative square root of 25. So non-negative numbers like 25 are going to have 2 square roots. Which brings me to an important point, because first here we said n greater than 0. But we're getting to the level where we have to be a little bit more specific, and since 0 does have a qualifying square root, we're not just going to say greater than 0 anymore. We're going to say greater than or equal to 0. And if a number n is greater than or equal to 0, we don't call it positive anymore. We say n is non-negative. That's a term that you're going to have to get comfortable with. What non-negative basically is a word we created out of respect for 0, because 0 is not positive, but it shares a lot of qualities that positive numbers do. So in order to include it with the bunch, we had to create a new name, and we don't use any space or anything like that. It's all one word, non-negative. So when you're dealing with non-negative numbers, they're all going to have square roots. All non-negative numbers other than 0 will have 2 square roots. 0 itself, if you notice, is just going to have one square root, which is 0 itself, because the only number you can square to get 0 is 0 itself. Okay, for this next problem, we'd like to find all the square roots of these numbers, starting with 81. Remember that we're going to have a principal or positive square root of 81, which is going to be positive 9, which we usually just write as 9. And we'll also have the negative square root of 81, which is going to be negative 9. And basically, the two square roots are negative 9 and 9. For 16 over 25, we handle it in exactly the same way. We get the positive square root of 16 over 25, which is 4/5, and the negative square root of 16 over 25, which will be negative 4/5. For a number like 7, which is not perfect square, best we can do is get an approximate value from our calculator. So we'll again get the positive square root of 7 and the negative square root of 7. So here we'll get an approximate value for that. Let me bring up a calculator. Okay, so we'll go ahead and use the square root button, which will be the second function of the square button, and we'll plug in 7. Your calculator should be able to handle this in a similar manner. So we get approximately 2.65. So positive 2.65 for the positive square root of 7 and negative 2.65 for the negative square root of 7. Now, even though it's not very easy to find the exact values of the square root of 7, it is easy to get a pretty good idea of what the number should be even without a calculator. We know that 7 lies between two perfect squares, namely 4 and 9, right? 4 is the largest perfect square less than 7, and 9 is the smallest perfect square greater than 7. So basically, because the square root is a one-to-one function and increasing, we know that the square root of 7 is also going to be somewhere between square root of 4 and square root of 9. In other words, the square root of 7 should be somewhere between 2 and 3. Now, if you look at a quick graphic, notice that 7 is 3 units away from 4, but 2 units away from 9, right? So this distance here is shorter than that distance. So when we find the square root of 7, a similar relationship should exist, and therefore the square root of 7 should be closer to 3 in value, not by a whole lot, but by some measure, than it is to the square root of 4. So this is why, which is 2. So, and we can see that play out here. Notice 2.65 is closer to 3 than it is to 2. Exactly halfway between 2 and 3, we have 2.5, right? So 2.65 lies somewhere around there. So again, we can do a lot of logical reasoning to get a good feel for where the square root of 7 should fall. But if we want the exact value, we'll go ahead and utilize a calculator. So there's actually a way of making a generalization here, which is the fact that if you take the square root of any perfect square, you're going to get some rational number. And here we're only talking about the principal square root. And the same goes with the negative square root. And if you take any square root of a non-perfect square, that answer is going to give you an irrational number. In fact, this is the easiest way to generate as many irrational numbers as you want, because all you have to do is take a square root and put a non-perfect square inside it, and you have yourself an irrational number. Now, if you remember, rational numbers are the numbers that can be written as either a terminating or repeating decimal, or another way of putting it is that they can be written as a fraction, m over n, where m and n are both integers. And of course, n should not be 0. And what is an irrational number? The exact opposite. It is neither terminating, so we say it's non-terminating, nor repeating. So you'll get a non-terminating, non-repeating decimal, and there's no way you'll be able to write it as a fraction of two integers. So not possible to write as a quotient of integers. So just a little technical and theoretical aspect of square roots. And of course, there is one other special case we can talk about, and that is, what if we want to talk about the square root of a negative number? Such as the square root of -4. Sometimes when you ask some students that, they're tempted to say, oh, -2, but that's not true, because remember, the square root of -4 means some real number that you square to get -4. And if you notice, if you square 2, you get 4. If you square -2, you also get 4. So there is no real number whose square root is -4. That's not to say that the square root of -4 doesn't exist. It exists and is part of a very important set of numbers which we will study later, called the set of complex numbers, but there certainly is no real number that you can square to get -4. So when you get this, for the time being, until we study complex number, all you're going to say is not a real number. And that's what you'll say for the square root of any negative number. You're just going to say not a real number. So we can extend the notion of square roots to higher roots as well. So for example, if I say to you, what is the cube root of 27. I'm basically asking you for the number that when cubed gives 27, and you know that that number is 3. Why? So why is the cube root of 27 3? Because if I take 3 and cube it, I get 27. So if I say what is the cube root of 8, some of you will know that that's 2. Why? Because if I take 2 and cube it, I get 8. Notice that while square roots of non-negative numbers other than 0 gave us 2 answers, with cube roots we get a unique answer. And one problem we had with square roots was that we couldn't have negatives under the radical, but here we can have negatives. Like the cube root of negative 27, what number do you cube to get negative 27? That would be negative 3. So why is the cube root of negative 27 negative 3? Because if I take negative 3 and I cube it, I get negative 27. In the same way, the cube root of negative 8 is going to be negative 2. Why? Because if I take negative 2 and I cube it, I get negative 8. Here, the index has changed to 3. So, what about the cube root of 125 over 64? Well, I ask myself, what do I have to cube to get 125? I know that's 5, and what do I have to cube to get 64? That's 4. So the cube root of 125 over 64 is going to be 5 over 4. And again, the reason is because if I take 5/4 and I cube it, I get 5 cubed, which is 125 over 4 cubed, which is 64. Now you can extend this to other roots as well. Like, what is the 4th root of 16? I think you've realized that with these even indices, you're always going to get more than one answer, unless of course it's an even index and you have a 0 for a radicand, in which case you're only going to get one answer. But notice the positive 4th root of 16 is just going to be positive 2, which we usually just write as 2. But notice there's also a negative 4th root of 16, which is going to be negative 2. And so why is the 4th root of 16 2? Because if I take 2 and raise it to the power of 4, I get 16. Why is negative 2 also a root of 4th root of 16? Because if I take negative 2 and raise it to the power of 4, I also get 16. So in the same way as with square roots, you're going to end up with 2 answers whenever the index is even and the number under the radical is positive. In the case of 0, like for example the 4th root of 0, of course you're only going to get one answer once again. Just as an example of a 5th root, you can have the 5th root of 32, and if you break down 32 using its prime factorization, the smallest number that's prime and goes into it is 2. We write that here, then we divide, we get 16. Again, 2 goes into 16 to give us 8. Once again, 2 will give us 4. One more 2 gives us 2, and finally 2 goes itself once. We can see that 32 is basically 2 to the 5, so it's a perfect 5th power. So what number is it whose 5th power is 32? Basically 2. Now it will be extremely beneficial to you if you memorize a few tables that I'm going to write down for you so that you don't have to run to a calculator every time you want to do some of these simple roots. So we'll do one for squares. That's going to be the longest one. So we'll start with 0. We know that 0 squared is 0. We'll do 1. 1 squared is 1. 2. We know that 2 squared is 4. 3 gives us 9. 4 gives us 16. 5 gives us 25. 6 gives us 36. 7 gives us 49. 8 gives us 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. Let's go to 12 for the squares, and that gives us 144. Now you may be thinking, we're doing roots, why are you giving us these power tables? That's because this is actually two tables in one. If you're looking from left to right, yes, you're looking at a power table. You're looking at the squaring table. But if you look from right to left, you're looking at a square root table, aren't you? Like, what's the square root of 81? 9. What's the square root of 144? 12, etc. So we'll do one for perfect cubes. Don't worry, it's not going to be as long. Let's just go to 1, 2, 3, 4, 5. We know that 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. Again, this is also a cube root table if you look from left to right. So if I say the cube root of 64, you know it's 4. If you memorize these tables, you're going to become quick and sharp like some of the people that you find so impressive in math classes. So let's do a few for x to the 4. Just a few for x to the 5. And a couple for x to the 6. Like x to the 4, we have 0, 1, 2, 3, and let's go to 5. It's good to know. 0 to the 4 is 0, 1 to the power of 4 is 1, 2 to the power of 4 is 16, 5 to the 4, think about it, that's like 5 squared times 5 squared, right? So 25 times 25, well, I'm getting ahead of myself. 3 to the 4 is like 3 squared times 3 squared, so 9 times 9, 81. 4 to the 4 is like 4 squared times 4 squared, 16 times 16. Any of you who has worked with computers, you know that's 256. 5 to the 4 is 25 times 25, which is 625. So the nice thing is these two use the same digits but in different permutations. Here for the fifth power, we'll just go up to 2. 0 to the 5 is 0, 1 to the 5 is 1, 2 to the 5 is 32. For the sixth power, we'll also just go to 2. So 0 to the 6 is 0, 1 to the 6 is 1, and 2 to the 6 is 64. If you memorize these tables, you're going to be very, very sharp as we proceed with our discussion of radicals. Next, I want to take a quick look at radical functions. Now, if we create a function and call it f of x equals square root of x, we become able to graph it because we'll go ahead and make a table of values where we use x as the input and y equals f of x, which is of course square root of x as the output. So remember that if we want to get real number answers, our x is going to have to be greater than or equal to 0. So the very first number that we can use in our table is 0. We don't want to use any negatives. And we know that the square root of 0 is 0. Now I could put any number for the input here that I want. As long as it's positive, it's going to have a square root. But I'm going to go ahead and be clever and just use nice perfect square ones, because that'll still give me a good graph. So I know that if I have 1, the square root of 1 is 1. The next perfect square will be 4, and the square root of 4 is 2. The next one is 9, and the square root of 9 is 3. The next one is 16, and that gives me 4. Even if I just graph these first few values, so 0, 0, 1, 1, 4, 2, 3, 4 gives me 2, and 9, so 5, 6, 7, 8, 9 gives us 1, 2, 3. So if we nicely connect these, we see that the square root function looks something like that. Notice it's what we consider to be a slowly increasing function. The values do increase, but not as rapidly as some of the other functions you may have seen, like squares or exponentials. And notice as far as the domain is concerned, meaning the x values that generate this graph, that's just going to be all the non-negative numbers. So we know that the domain is the set of all x such that x is greater than or equal to 0, which we can write as an interval as bracket, comma, 0 to infinity. And the range is going to be also, notice what are the outputs. If you look at all the y values that generate this function or are associated with this function, they're also start here and go up. So the range is gonna look almost the same, but it will look different in this set builder notation, because instead of saying all x such that x is greater than or equal to 0, we're going to say all y such that y is greater than or equal to 0. And we're going to write it as the same bracket when it comes to interval notation. So notice the interval notations for the domain and range are the same, but in set builder notation you can see the difference because of the type of variable that we use. And that's how you graph square root functions. There's only one other thing I want to talk about before we say goodbye today, and that is an expression of this form. Okay, that's an expression you have to be careful with, because you may be tempted to say, oh, you want to know what number squared gives x squared? Well, that would be x, right? Well, that depends, because yes, if I say to you, what is the square root of 3 squared? You can say, okay, that's the square root of 9, so it's 3. So with that logic, you might be thinking, well, why can't we say the same thing here, that the square root of x squared is just x, right? Well, here's the problem. What if I ask you what is the square root of quantity negative 3 squared? Notice quantity negative 3 squared is also 9. So this is going to be the square root of 9, which is going to give me 3 as well. So how do I make sure that when I don't know the value of x, I don't get into trouble and put the wrong answer here? Because obviously if x is going to be negative, the answer is not going to be itself, but it's going to be its opposite. So if you remember, we have a perfect function that deals with that. So when we don't know the value of x and we're not sure that x is non-negative, the way we handle the situation is we simply say it's equal to the absolute value of x. And now it's safe, because if, let's test it with these two situations. You have the square root of 3 squared. Well, according to this rule, that's just going to be the absolute value of 3, which no problem, we know that's 3. But what if I have square root of negative 3 squared? Will this rule handle it properly as well? Notice that's going to be the absolute value of negative 3, which is 3. So unless the problem specifies that the variable is non-negative, you're going to need to use absolute values when you deal with the square root of x squared. So, for example, if I say to you to simplify the square root of y cubed, and I don't make any specifications about, so I just want you to simplify, and I don't tell you anything about the value of y, right? So you realize you can actually break that up in this way, right? But here, for the square root of y squared, you're going to write the absolute value of y, and then multiply it by the square root of y. So this will be the proper simplified version of the square root of y cubed. And you have to leave the absolute values, since we don't know that y is greater than or equal to 0. Now, if I gave you the same problem and I said simplify and assume y is greater than or equal to 0, then you're going to say the square root of y cubed equals the square root of y squared times the square root of y. And this time, because y is non-negative, it's going to fall into a category like this. So it is going to be this, the square root of y squared is going to be y. So you can start out with the absolute value of y times radical y, but you know that the absolute value of a non-negative number is itself. So this time you can actually go further and say that's equal to y square root of y, like that. But remember, that's only if you know that y is greater than or equal to 0. What if we said simplify negative square root of u to the 6? Now you know that the expression you have to square to get u to the 6 is u cubed, right? But the problem is that u cubed could be negative. So here we're going to say negative absolute value of u cubed, right? The negative is just carrying. Now we can do a little better than that, because we can say that's negative absolute value of u squared times the absolute value of u. Now u squared is definitely going to be non-negative, because when you square any real number, you're going to get a non-negative answer. So this part here, you're dealing with the absolute value of a non-negative number, which is going to be itself. So you're going to say negative u squared, but you do have to keep the absolute value under u. As one last example, consider the square root of x to the 4. Again, no specific instructions given on the value of x, so we have to assume that it could be negative. But notice that as you know, the expression that has to be squared to give us x to the 4 is x squared. So here, according to the rule from the previous page, which said, hey, if you have the square root of x squared, you get the absolute value of x, and we know this is going to be the square root of x squared squared, so we should get the absolute value of x squared. However, here it's okay to get rid of the absolute value because, as you know, x squared is greater than or equal to 0 for all x belonging to the set of real numbers. So again, you're dealing with the absolute value of a non-negative number. Remember, you don't want to say positive here, you want to say non-negative. And therefore, we know that it's going to be itself. There you have it. So that's a quick introduction to the concept of radicals and a quick look at the square root function. And that should do it for today. So take care and be safe until the next time that we meet.